everyone, my name is Rahmani from University of Maine, and I'm going to talk about first direct evidence for presence of sulfur-induced deep electron and hole traps in titanium. Photocatalysis is considered to be one of the cleanest technologies that has been used in medical, environmental, and energy applications, and possibly it's going to be a key factor in fighting with global warming. One of the well-studied photocatalytic material is titanium. The ability of titanium to absorb solar photons and create charge centers on the surface as reaction sites with sufficient redox potential for chemical transformations like water photolysis for hydrogen production makes this material an excellent platform for developing new photocatalytic systems. Here, an incoming photon would excite an electron from the valence band to the empty states of the conduction band, creating an electron-hole pair as the charge centers. To illustrate the titanium band diagram and photoexcitation of electrons, I have invented a weird version of a pinball machine. The bottom part, which is filled with balls, represents the valence band. The empty upper part as conduction band, and the middle black section is an energy barrier. As a rule of this game, no ball can exist in the energy barrier and they can just pass it if we flick them with enough energy. In reality, this 3.2 eV energy gap limits the photocatalytic activity of titanium to just less than 10% of the solar energy received on Earth. This is like in the most of the times we are just poking the balls without enough energy. In several studies, it has been proposed that doping titanium with sulfur would resolve this issue. Quantum calculations have shown that replacing lattice oxygen or titanium atoms with sulfur could create filled electronic states above the valence band maximum, increasing the Fermi level, resulting in a narrower band gap. Also experimentally, the presence of these sulfur-induced states has been shown using valence band XPS in sulfur-doped material. With these new narrower band gaps, a lower energy photon in visible region could also kick an electron into the conduction band, creating an electron-hole pair. This is known as band gap narrowing effect. This is like we are adding new ball reservoir in the black region and we don't need to flick the balls hard as before. In reality, because of this effect, a bigger portion of the solar spectrum could result in charge separation and theoretically, it could improve the photocatalytic activity of titanium. A photoexcited electron is in a metastable condition and eventually it would recombine with a hole in a picosecond timescale. This short lifetime is an important reason for the low quantum efficiency of common photocatalysts. Based on literatures, in addition to band narrowing, sulfur states could act as electron traps and by capturing the excited electrons and interfering in the recombination mechanism, they could increase the charge center's lifetime and increase the chance of surface reaction. Most of the experimental evidence for electron trapping behavior in sulfur-doped titanium is based on the lower intensity of the first relaxation peak in photoluminescence spectrum. This peak is due to recombination of electron hole pairs and electron entrapment could result in lower intensity. This reduction in the intensity has a correlation with sulfur content. But there is a concern here. If we go back and see it from another angle, the reason behind of this observation could be because of a hole entrapment. The limitation of this technique on distinguishing between hole or electron traps makes these claims very speculative. There is also another inconsistency here. To have these states acting as trap, they need to be unoccupied or partially occupied. But previous calculations are showing fully filled electronic states contradicting with electron trapping behavior of these states. In this work, we use a unique approach to confirm presence of electron traps without the need for distinguishing between hole or electron entrapment. Hydrogen dissociation on a clean, dry, and dehydroxylated surface produces electrons. These electrons would populate lowest empty electronic states either in the conduction band or in any mid-gap states. In addition to electrons, water and oxygen vacancies are byproducts of this reaction. This is look like we are adding extra balls to the upper part of our pinball machine. Now, if we have any empty or unoccupied states in the band gap, these electrons will populate them and we can determine their energies spectroscopically. A typical experiment includes two main steps, pretreatment and hydrogen dissociation. In pretreatment step, we increase the surface temperature stepwise under a very dry oxygen gas flow to prepare a dry and dehydroxylated surface without any carbon contaminants. During this step, we monitor the surface using diffuse reflectance IR spectroscopy. On the beginning of step 2, we collect a single beam spectrum as reference under dry argon environment at 300 Celsius. Right after argon flush, we flow hydrogen over the titanium surface to produce electrons and monitor it continually with IR or UV visible light. After collecting spectra under hydrogen, an argon flush step is used to prevent the mixing of the remaining hydrogen gas with oxygen. The last sequence of this step 2 is to reoxidizing the surface. In this study, we looked at two pure titanium materials, P90, which is synthesized at high temperature with low defect density, and homemade pure low temperature synthesized anatase, which has higher defect density. For sulfur-containing material, we use commercial anatase from 4 different vendors. The sulfur content in this material was over 1000 ppm. After switching the gas flow from argon and exposing the P90 surface to hydrogen, surface hydroxyl groups were reappeared as the sign of production of electrons. At the same time, a broad background absorbance was developed under hydrogen and it was stable under argon flow. The broad background absorbance was disappeared quickly under oxygen flow. The shape of the background absorbance, which increases toward lower wave numbers as a power function, is a sign for presence of electrons in the conduction band. The absence of any significant absorbance in the UV visible region of the spectra shows that there are no unoccupied electronic states available for electrons in the P90's band gap. We observed appearance of hydroxyl groups and development of broad electronic absorbance under hydrogen for our homemade pure anatase. The electronic feature was stable under inert argon, but oxidizing the surface removed the accumulated electrons very quickly. In BC's case, we observed a step-like electronic absorbance with the threshold at about zero point 0.2 eV. This is comparable with de Valentine's report that lattice defects could create electronic states 0.3 eV below the conduction band minimum. Here, shape of the electronic absorbance suggests that electrons are populating these shallow traps, and IR photons with energy higher than 0.2 eV could excite them into the conduction band. Absence of any significant absorbance in UV visible region suggests that there are no deeper electron traps in the band gap. In sulfur-containing samples, we did not see the electronic feature in the IR region, but we observed a strong absorbance centered at about 24,000 wave number under hydrogen. This feature was stable under argon and it quickly disappeared by reoxidizing the surface. These observations, for the first times, are showing that there are electronic states acting as deep electron traps 2.8 eV below the conduction band minimum. Electrons in these states are out of reach of IR photons, but photons in UV visible region could excite them into the conduction band. Comparing the results of 4 different commercial anatase samples with pure material provides the first direct evidence for the presence of sulfur-induced deep electron traps in titanium. Monitoring the surface with FTIR during pretreatment step shows that the bidentate sulfate-like species transfers into tridentate structure at 300 Celsius while the surface is dehydrating. Our finding shows that there are no deep traps created at this point. Heating the surface further at 400 Celsius results in reconfiguration of sulfate-like structures and creation of lattice-substituted sulfur. In all cases that we observed deep traps, sulfur was present in this form. These findings are suggesting that the origin of these deep electron traps is sulfur atoms substituted to the lattice. Our band diagram calculation results are backing up the experimental findings, showing that sulfate-like structure is not creating any electronic states in the band gap. But sulfur sitting on titanium or oxygen sites in an oxygen-rich condition results in creation of partially filled states above the valence band maximum. There is experimental evidence in the literature that showing holes created under UV radiation in sulfated titanium has lower oxidation potential because of hole entrapment in sulfur states. By considering these reports and our evidence for deep electron traps, along with XPS results that showing signals for sulfur with 6 plus and 4 plus oxidation states, we can imagine a dual nature for sulfur states in titanium. These states could act as electron traps by accepting electrons from conduction band and reduce to 4 plus oxidation states. And then, by donating electrons to the holes in the valence band, they can act as hole traps and reoxidize to 6 plus oxidation states. And that's bring us to the end. I want to thank you for watching this presentation. Also, I want to thank my advisor, Dr. Frederick, my friend, Dr. Mahtabi Shakib, our collaborators, and my friends in Human Catalysis Group. Also, a special thank to those awesome people who coordinated PEC 2021.